Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 31, Organic Chemistry 2. Today we will continue on chapter 7, Carboxylic acids. We will talk about reactions of carboxylic acids, reduction of carboxylic acids. Let us start the lecture with a question. A carboxylic acid has two oxygen atoms, each with two non-bonding pairs of electrons. Draw the resonance forms of carboxylic acid that is protonated on the hydroxyl oxygen atom. Compare the resonance forms with those for an acid protonated on the carbonyl oxygen atom. Explain why the carbonyl oxygen atom of a carboxylic acid is more basic than that of the hydroxyl oxygen. Well, let us answer point A. Here we have the carboxyl group. We have two oxygen, each with two lone pairs of electrons. If this oxygen is protonated, we get this O+, and one more resonance structure where here is negative and here is positive. We have here two adjacent positively charged, so this resonance structure is unfavored. Okay, two positive charges are adjacent to one another. So let's go to protonation of the oxygen of the carbonyl. We get this OH bond, positively charged here, resonance structure when we have the positive charge in here, delocalization of this one lone pair to form double bond, and positive charge in here. So as we can see, clearly protonation on the carbonyl oxygen provides three resonance forms, distributing the positive charge over three atoms with no additional charge separation. Well, if we compare A and B resonance structures, the carbonyl oxygen will be more basic. By definition, it reacts with the proton to give more stable, what we call weak conjugate acid, than that of the protonation of the hydroxyl. So, if we say that this is a base and this is a conjugate acid, here the conjugate acid is more stable, so it is weak acid. Now we know which oxygen will react first as a base or a nucleophile. We will talk about the substitution of the hydroxyl hydrogen, like the net reaction of the carboxyl with an electrophile. The net result will be substitution of this H with an E. And let's see how the reaction goes. If E is a strong electrophile, it will attack the nucleophilic oxygen of the carboxylic acid directly, giving a positively charged intermediate, which then loses a proton. Reacting carboxylic acid with an alkene in presence of catalytic amount of acid provides an ester. The process will start by protonation first of an alkene to form carbocation intermediate. this oxygen lone pair will then attack on the electrophilic center to form this positively intermediate, which exists in three resonance structures. Deprotonation furnishes the ester. So the net in here is replacing the hydrogen with the tertiary butyl group. If E is a weak electrophile, such as an alkyl halide, it is necessary to convert the carboxylic acid to the more nucleophilic carboxylate anion to facilitate the substitution reaction. So we will take the carboxylic acid, treat first with sodium hydroxide to form carboxylate. Here we have O minus, so this species is more nucleophile, will attack on the partially positive Lie center and kick the X minus out and form the ester. Reacting diadomethane also with carboxylic acid provide methyl ester. First, this hydrogen, acidic hydrogen, will react with CH2 minus to form CH3 N2 plus, and carboxylate. The carboxylate species will attack on the CH3 carbon and get rid out of the N2 to form methyl ester. Substitution of the hydroxyl group. Reaction in which the hydroxyl group of the carboxylic acid is replaced by another nucleophilic group are important for preparing functional derivatives of carboxylic acids. So we are replacing the OH by different nucleophile. Fissure estrification is an example. Converts carboxylic acids and alcohols directly to esters by an acid catalyzed nucleophilic acyl substitution. Nucleophilic acyl substitution. The net reaction is replacement of the OH with OR of the alcohol. Here is the carboxylic acid, here is alcohol, H plus catalyst. We are going to take this OH out and replace it by OR prime. Ester. The first step, protonation, okay, with the resonance structures. Then the lone pair of the oxygen atom from alcohol will attack as a nucleophile. Nucleophile attack. To form this species, we will take H from here and transfer it to one of these oxygen to here. So we can write minus H plus H plus to form this species where the positively charged transfer from here to here. This process will take place via alcohol molecules So ROH will take this H, became ROH2 plus, and then come nearby this oxygen and transfer the proton to it to form this species. Now this lone pair will come down here and kick molecule of water out to form that species. Loses of H plus provide the ester. This is a mechanism, what we call it Fissure Estrification, and it goes through nucleophilic acyl substitution mechanism. Amides can be synthesized directly from carboxylic acids using heat to drive of water and force the reaction to completion. Carboxylic acid with amine acid-base reaction to form salt. Heat, you get the amide. This reaction takes place usually in non-polar solvent like benzene, toluene, where the carboxylic acid exists in dimer. So we can propose that in dimeric, in non-polar solvent, the dimer structure is in equilibrium with the monomer that reacts with amine to form the salt, or in its dimeric structure react with amine, proton transfer, as we see here, proton transfer, with nucleophilic attack to get out acid, and this compound which lost losses water to give an amide. You can read more about this mechanism in European Journal of Organic Chemistry 2011, page 5981. Elimination of water. So to drive this reaction forward, we have to get the water out of the system. In the lab, we can use the Dean-Stark trap. It's a special piece of glassware which allows the collection of water during the reaction through what we call isotropic distillation. The desire to collect water from the reaction can drive the equilibrium in reaction where water is formed as a byproduct. So we heat the reaction mixture in here. Water coming out of the reaction will mix with the toluene or benzene, get out in here, condense back to here. As you can see here, water will be the bottom layer, and the toluene or benzene will be in here, and the excess will go back to the reaction mixture. By this way, we get the water out of the reaction. They call it Dean-Stark trap method. Carboxylic acids can be converted into acid anhydrides with excessive heating or treatment with phosphorus pentoxide. Two molecules of acid with the loss of water gave acid anhydride. Well, the first step in the mechanism is proton transfer to form the carboxylate, followed by nucleophilic attack like SN2 mechanism, then again nucleophilic attack. This is nucleophilic acyl substitution, and then deprotonation to furnish the anhydride. Carboxylic acids can be converted into acid chlorides with thionyl chloride or oxalyl chloride. Well, reacting acid with thionyl chloride or oxalyl chloride provides acid chloride. First step, again, nucleophilic attack. This species will be in resonance. We have two resonance structure, followed by loss of Cl minus, then Cl minus nucleophilic attack, elimination of HCl and SO2 to furnish acid chloride. So these two electrons forming double bond, cleave this bond and forming here double bond with the loss of Cl minus with H plus, forming HCl, SO2 here, and then leaves acid chloride. Reduction of carboxylic acids. Lithium aluminum hydride reduces carboxylic acids to primary alcohols. The aldehyde is an intermediate in this reduction, but it cannot be isolated because it reduces more rapidly, more easily than the original acids. So carboxylic acid with lithium aluminum hydride, first step in ether or THF, then followed by acidification to furnish the alcohol, primary alcohol. The first step is proton transfer to form again carboxylate, followed by nucleophilic attack, then elimination of this group to give the aldehyde, which reduces faster, very fast, to give again the salt, which hydrolyzed in the final step to furnish the alcohol. Borane also reduces carboxylic acids to primary alcohol. Borane complex with THF usually is the reagent, reacts with the carboxylic group faster than with any other carbonyl function. It often gives excellent selectivity. So we have carboxylic acid, again borane complex with THF, then step 2, acidification to furnish alcohol. We talked about selectivity. We have in this molecule, we have two function group. We have carboxylic group and we have carbonyl group, ketone. With borane, selectively we reduce this to a primary alcohol and keep the ketone untouched. Okay? The mechanism starts with Lewis acid Lewis base complex formation, followed by another Lewis acid Lewis base. Then the same type of reaction will occur on these hydrogens to form O-acyl on the borane, followed by again Lewis acid Lewis base with third molecule of borane, and the formation of four-member ring, then nucleophilic substitution, followed by elimination of these species and hydrolysis to form the alcohol. Reduction of carboxylic acids to aldehydes is difficult because aldehydes are more reactive than carboxylic acids, our most reducing agents. Almost any reagent that reduces acids to aldehydes also reduces aldehydes to primary alcohols. Lithium tritertiary butoxy aluminum hydride is a weaker reducing agent than lithium aluminum hydride. It reduces acid chloride to aldehydes because acid chlorides are strongly activated toward nucleophilic addition of hydrides. So carboxylic acid with thionyl chloride to acid chloride, then we can reduce acid chloride to aldehyde using lithium tritertiary butoxy aluminum hydride. Show how you would synthesize the following compounds from the appropriate carboxylic acids and acid derivatives. How you can get this primary alcohol from this carboxylic acid? Well, they have the same number of carbons, 2 carbons, 2 carbons, so we can just reduce the carboxyl group using lithium aluminum hydride, followed in second step hydrolysis. Here we have the alcohol. If you would like to get this aldehyde from carboxylic acid, so what we have to do is the same number of carbons, okay? All what we have to do is take the 2-phenylacetic acid with thionyl chloride to form the acid chloride, then use lithium tritertiary butoxy aluminum hydride as a reducing agent to get the aldehyde. How we can get this compound from 3-hydroxymethyl cyclohexane 1-on? Well, we have here carbonyl ketone and we have carboxylic acid, and we get in here is only reducing this carbon to alcohol and keeping ketone intact. To do that, we use borane, then followed by hydrolysis. We can do the same by first protecting the ketone acetal formation using glycol in catalytic amount of acid, then reduce the carboxylic acid with lithium aluminum hydride, followed by hydrolysis and warming to hydrolyze the compound to the alcohol and break back the acetal to the carbonyl. See you next lecture.